My name is Chris Wise. I'm an engineer. I'm an engineering designer, and I'm an engineering teacher and professor. Well, I've worked for 30 years in engineering all over the world. Lots of projects, including this one behind me, the Millennium Bridge, which we did about 10 years ago. I've worked on a tower in Barcelona, which is the same height as the Eiffel Tower, 300 meters. The first green skyscraper in the world, which is in Frankfurt for a bank, lots of stadia, airports, all those sorts of things. Well, when you're designing something very, very large and you're making something very, very large, it's very easy to rapidly be swamped by natural forces. So gravity is the principal one. Things become very heavy very, very quickly. So you're talking about thousands and thousands of tons of material that you have to deal with. So even just sitting it on the ground becomes a major undertaking. You have to think about in something as large as a pyramid, you have to think about whether or not it will fall down under its own weight, whether it will fall down with an earthquake if an earthquake hits it, whether it will settle and the ground will give way underneath, or maybe in the corner. And also you have to be very careful if you introduce a break line inside the structure. You have to make sure that you don't introduce a zone of weakness where one side can move relative to the other. So, and of course that's exactly what they did. So it's important to very carefully consider the whole thing all the time and not to focus too much on one little detail, because if you do that, nature has a habit of reminding you very quickly that you've forgotten about gravity, or you've forgotten about and even on this bridge, and we studied everything we could possibly think about, and when the people started walking across the bridge, we'd forgotten one thing and the bridge started wobbling, which is, for a designer, is quite a scary experience. If you built a pyramid and it started to fail, I think you would be a dead man very quickly. I have two young sons, and when they build things, they don't do a drawing. They just start, and as they work through, they respond to what they've built and they add things, and eventually it falls down. I think when you're talking about something like the pyramid, it would be very, very foolish to start without having a major understanding of the whole structure at least in your head before you start. If you are starting to have lots and lots of pieces made for you for this project that are coming from other places, or even from close by, with maybe hundreds or thousands of people cutting pieces of stone, it's very important that they know how big they have to be and that they're going to fit together. They don't have to make too many adjustments when they get them to their final position. So somebody somewhere has to be able to guide them through that process. And nowadays we use computers and we use drawings. In medieval times they used to draw full size on the floor, and I can imagine in Egyptian times they may have had a sort of master plan which may have been full size set out on the side, and then for the individual stones they may well have had a series of templates or guidelines within which people could work to enable them to make the pieces. But you have to have an overall master plan, otherwise it would fail. And I think it's particularly, you go from the generalities of the whole structure through to the precision of the individual chambers, the tunnels that make the access, and eventually to the sarcophagus, becoming more and more precise as you go through. And I think that degree of thinking needs to be enshrined right from the very beginning, otherwise it will fail when you get there. Well, the human eye is very precise, and so it's quite common. It was common in many sorts of technology for people just simply to put 2 points some distance apart and just look straight through. And it's also possible to make things level but the traditional way of doing that was to use water. So you would make a channel, you would run water from one end of the channel to the other, and when the water was level, you knew that was level. So I think it would be relatively easy personally to set out the base on the ground and to make it level. It's harder when you're thinking about aiming for a point up there to make sure that you're going to set it up precisely so that they all finish at the same point. And I could imagine, for example, having a point on the ground, and you could then say, right, we build something, I don't know, 20 meters up over there, and we take a line through there, and you need one from each corner, all going to the same point. And that's extremely difficult to achieve. So I don't think that that's a credible solution. I think they would have probably had to use each surface as the setting out for the next one, so that you would use the work you'd already done, start again at the next level, and then work your way up gradually. And they would check back to the work they had already done, so they would get a sense as to whether or not they were being precise. It's also, I don't know if the fact that they clad the pyramids in marble, whether or not that would be much easier to do, because you already have something very close to where the final position of the marble is that would enable you to measure or to check angles much more accurately. So by choosing to put a finishing skin on the pyramids, they allowed themselves some adjustment. So it's actually quite a clever technique, because it's similar to the sort of thing you do in modern buildings, where it's quite common to build a frame and then come along later and add the glass and the steel to the outside and adjust it until it's perfect. The skeleton inside doesn't have to be so perfect. I know many people say that the way that they got the stones up to the top of the pyramid was to build a large ramp. Personally, I don't think that's a reasonable proposition. And the reason I don't think so is because to get a gentle enough gradient to be able to pull stones that weigh several tons, you're looking at a ramp that starts a kilometre away or a kilometre and a half away, and as you get taller and taller and taller, the ramp gets bigger and bigger and bigger, and you need so much material to make the ramp. You would need hundreds of times the amount of material that you would need to build the pyramid, and it just doesn't seem to be sensible. So they must have had some other way of doing it. I think you can rule out a large ramp that comes from a long way away. I don't think that's possible, because it requires too much material. So you'd be looking for something which is much closer to the pyramid itself. And of course, the best thing to do is to use the pyramid itself as a support structure. And it's a stepped structure. So you have the possibility of making a more gentle incline built off those steps, and to use those to make the next level. That's a possibility. You run into trouble. There are many problems with that. The first one is that the width that you have for your ramp, the step might be that wide, a metre wide or something, metre and a half, I don't know. And if you make the ramp a metre and a half wide, you have to be able to pull the stones up there, and have all the people on it, and have all the machinery you need, or rollers or whatever they are, without falling off the edge and falling down to the bottom. So it would be a very, very confined operation to do it. So I suspect they wouldn't have done it off a single step. They would have done it off two steps maybe. So you're looking for a broader ramp, perhaps supported locally, off maybe 2 or 3 steps. So something 3 meters wide would be a reasonable proposition to make. If you imagine you're a child and you're trying to make a big pile of something, then you wouldn't just do everything from the outside. I mean, I agree that it makes sense simply to get as close as you can to the position that you want to put your material. So, of course, the outside part has to be done with ramps on the outside. But I think when you're talking about something that's more than 200 meters across, of course you would be working from the inside as well. So I don't think it's unreasonable. I think it's a good idea to imagine that at least for the lower part, they would have been working from the inside out as well as from the outside in. I think that's quite likely. I don't know much about Egyptian instruments, but if you're trying to measure an angle, you need to decide what the angle is in the first place. So I imagine somebody would have made a model of this thing, a small model, and they may have just, it might have been 10 meters high or something, and taken a sort of scaled up version and used that for the real pyramid. If you know the angle, then you can set yourself a template, which can be very simply made of 2 pieces of wood virtually, or 3 pieces, to make the angle, and which you can then look along. At which point you have a way of checking the geometry. I think on something like a pyramid, you would be looking for not just looking up the corners, but you're also checking that the sides are where you want them to be as well. So you have to check the diagonals, the distances, to make sure. Now the Egyptians probably knew that for a square, the two diagonals were the same, because even if they couldn't do it mathematically, they would have found that out by trial and error. And they clearly had a very good understanding of geometry. So I think they could have made themselves some fairly simple pieces of equipment using timber, perhaps water for level, which would have enabled them to do the basic geometrical checks. And they would have... Okay. It's okay. No, it's okay. I think it's quite possible the Egyptians could have made themselves a set of fairly simple instruments that would have been able to measure angles, would have been able to measure distance. And if I was doing it myself, I would definitely be looking for a double check on every single measurement, because you really don't want to move hundreds of tons of stone and then find out that it's in the wrong position. So you're always checking the diagonals and checking the alignment at every stage. If you want to make a perfectly accurate building nowadays, the best way to do it is to use light as the measuring device. And so people now use lasers all the time to check level, distance, and angle. And in the old days we used our eyes, but now we use light beams. And I think it's, of course, the Egyptians didn't have light beams, so they had to use something else. Well, it's interesting. If the Egyptians were more accurate in terms of their choosing their orientation than people 2,000 or 3,000 years later, I mean, firstly, it's very impressive. Secondly, it's possible they had a clearer understanding of the way that the sky behaved, because they lived under it all the time, than in more recent centuries, I think. And I think that you need to understand with Polaris that it isn't at the north, it's just off north, and it actually does rotate around. Now, whether it's possible to, I could imagine if you were trying to say, I wonder if that is north, you could align 2 points, you look at it and you look at Polaris, and you would realize, if you looked at it for a year, you would realize that it moves. And you could then realize that it moved a certain distance one way, a certain distance another way, a certain distance another way, and you could perhaps say, right, you wouldn't call it north, you would just say that's a magical point, and
Yes.
it's in the center of that, and that's what we aim for. I can imagine it's possible. It would take you a year, at least a year, to realize that it was even moving, and then you aim for the middle. If you're trying to measure something against the heavens, firstly, you need to understand where the things are and what rotates around what. Once you understand that, then you have to be able to measure it. And I think that making one single measurement is a very dangerous thing, because even now we can't measure things absolutely precisely. And when you're trying to get very precise angles in difficult locations, it's a hard thing to do. I think that it's much easier to take lots and lots and lots of measurements and then take the average of them. So I don't know how they did it in the 18th century, but if they were only taking a few measurements, the chance of making a mistake was much higher. Also, if they were taking a measurement that was based on time, a specific time, and I don't know if they were, but if they were looking for 12 o'clock on the solstice, for example, there's an error in the timing that also has to be built into the equation. So the fewer things you have to measure, the better, and the more times you measure it, the better. So maybe that's what the Egyptians did. If they managed to make a measurement of over 200 meters to an accuracy of a few centimeters, I mean, firstly, we would struggle to do that now, to be honest. I think they were helped by the fact that the things they were measuring were very stable thermally. So if you're measuring rock doesn't move very much when the sun comes out. It takes a long time to heat up, a long time to cool down, and so it stays where it is. If you're measuring a steel building or a glass structure or an aluminium structure, they move a lot as the temperature changes, and it makes it much harder. For example, if this bridge just between the summer and the winter, it cools down in the winter and the bridge goes up by 300 millimeters. In the summer it warms up and it goes down by 300 millimeters. So it moves around in response to temperature. To imagine measuring 200 meters or more, you have to say what was it what were they using to measure? I mean, did they have you can't measure it with rope, you can't measure it with wood, you can't measure it with metal because the metal will expand and contract. You could measure it with more pieces of stone. So it's possible, I don't know, but it may be that they were using stone as a measuring device because it was very stable. The other possibility, and I don't know how sophisticated they were, but I can imagine that you can set these things out much more accurately by measuring angles than by measuring distances. And so there is a possibility that I could imagine that they would, and I'm trying to imagine how you would do it, but I could imagine a series of reflections, light reflections, for example, where you would bounce the sun around, and that would if they had the technology to make themselves a simple mirror, you can pick the sun out and you can move that, at which point that line stays where it is and will not move. So it's possible, and if you do more than one check, then where the lines intersect, that's your point. Maybe they were using light instead of in a simple way, as we do nowadays, which I think would be very interesting to think about a bit more, actually. If somebody ordered a large pyramid, 3 large pyramids, I would well, you have to think about the material. So you do a simple calculation to work out roughly how much material you need, and you realize it's a lot. Then you have to work out some construction method, which, as everybody knows, is not the simplest thing in the world when you're moving hundreds and hundreds of tons of material. And the next thing you would be asked for is a price, probably. Which would be really hard to give anybody, because it was an experimental project. I mean, at the scale you're talking about, no one had ever carried out such an experimental project before, and I think that it's always extremely difficult when you're doing groundbreaking projects like this one, or like the pyramids, to attempt to imagine that you know everything at the beginning that you need to know as you're building something. So you can do rudimentary calculations about resources, you can do rudimentary calculations about the method. You need a very, very good source of materials that is never going to dry up. So you would have to go around and investigate all over Egypt to find sufficient quantities of material of the right quality to be able to be used for the main pyramid and then for the skin. The next thing you need is a supply of skilled craftsmen to make it, because it's one thing saying I'd like a nice statue in my garden. You can go and find one craftsman who can make it for you, but when you're talking about something so huge, you need lots and lots of people of quite a high caliber, simply because there are so many pieces to be made, and each one takes a long time. And particularly if you're working by hand, or using animals perhaps a little bit, but basically by hand, it takes much, much longer than it does nowadays. So I think that you want to, thinking forwards a little bit, you would probably start to think in terms of setting up a training school for people who are going to be working on the project, so that you take very skilled people and you get them to teach lots of others so that they can all work. So it becomes a life's activity or a career to work on the pyramid, and you're trained specially for that one job by somebody who is an expert. And I think that's the only way you would get enough people to work on it. You can't just go to the nearest village and say, right, give me 100 masons. They haven't got them. You've got to train them. If I was doing something for the first time in ancient Egypt, I mean, what I would try to do is that I would look for the closest example. And so I would look for the next biggest pyramid or the next biggest sculpture, and I would go and try and talk to the people who had worked on that project. If you're looking for expert help on making something as large as the pyramid, you need a builder, somebody who understands all the aspects of building, and that goes through making the pieces finding the pieces and taking them out of the ground, transporting them. You need somebody who understands about assembly and who understands about
It's a joke.
So if you try to make a very large project like the pyramids, you need to be an expert builder basically, and instead of the modern sense of building where it's all divided into individual little disciplines, you would need to have a very good overview of the whole thing, and that would include understanding where to get the material and how to buy it, how to extract it, how to move it to the site, how to fashion it and carve it into the right size stones to go into the pyramid, for which you would need a very large labor force, thousands of people. You need somebody to be able to work out a system for building it, and that could be one person. The system, the thinking could be one person. You need a way of controlling the dimensions, so you would need, and because it's a large project, you need people in each corner and probably maybe in the center, so you would have a series of gangs of people operating a dimensional control system, and people moving between them so they could talk to each other, so that if they had to change, that it was an easy job. Then you need somewhere for them all to sleep, somewhere for them to eat. You need people to cook for them. So there are whole series of it's like an army. You have to have everything you need to make the pyramids, and then everything you need to support the people who are doing the making. And so it becomes a sort of exponential growth. So if I do a calculation in my head that says we need 5,000 masons to cut the stones, that probably translates to 10 or 15,000 people by the time they have their families and their food. If you build in all the transport and everything else, you're talking about, I don't know, 50,000 people, maybe more, involved on that project. And that's a medium-sized town just devoted to one project. But if it's that big a project and that's important to the whole country, that's important to the pharaoh, then 50,000 people, it may not be so many. If you have 3 pyramids, you need 3 times the size of the organization. I mean, the thinking about how to build it would translate from one pyramid to the next. And also, it's quite common in construction to use gangs who are specialised in particular sorts of work. So once they've done the basic setting out for one of them, they would move on to the next one. So the real special skills, you have only a few people, but they move from place to place to place. And the man in charge or the woman in charge may well have been responsible for all 3, because the technology would have been the same for each one. It would be virtually impossible to do something like the pyramids without having a plan and without having a very clear understanding of your design. And you would have a client, the pharaoh is the client, and you would need to make sure that they agreed with what your plan was as well, which is very important. Whether they had drawings as such, I'm not so sure. They may have used models, I think, 3-dimensional models, which would have been more useful and more helpful. But they would have had to have some very clear understanding before they started of what it was they were going to do. You couldn't just start and hope it was going to work out all right. The long gallery is like a conjuring trick. To me, it's like magic, a piece of magic, because unless they built that first and then built the whole pyramid around it, which is possible, I don't see how it could have been done. Now, of course, you could start from the ground and gradually reach the point where you have the gallery, and then corbel up and carry on. And that would be possible. You would have to be, well, I was going to mention the sarcophagus. We know about can I talk about that? About getting the sarcophagus inside? Yeah.
Du sarcophage? Oui, bien sûr.
Okay.
Du coffre, en fait.
Yeah. Yeah, so I think one possible solution is you start from the bottom. You know well in advance that you're going to have a gallery, you're going to have the chambers, precisely where they're going to be. And when you get to that point, you put in the granite blocks, which are very specially made. I don't know about the minds of the Egyptians. It would be also a demonstration of control over their technology. You know, it's a statement of power and a statement of precision, and the fact that the borders of those chambers and of those tunnels were so beautifully made and so precisely made is a statement of capability. You know, it's a status thing. Usually in stone structures, it's not the crushing of the stone that is a problem. It's very unusual for stone buildings to fail by crushing of the stone, especially if they're large monumental pieces like the pyramids. It is possible for little pieces to fall down. So if you think about mine shafts and people digging out coal and things like that, they always had to put something horizontal to hold the roof up. The walls will stand vertical, but the roof needs some support. And of course, just using a simple piece of granite is very poor in tension. So it will, if you put a piece of granite across, it will simply break. It breaks its back under its own weight before you put anything else on top of it, to be honest. The natural form, the natural flow of forces in masonry structures like the pyramids is to take an arch, is to form a natural arch. And so if you don't know that and you build a structure, the bits inside the arch will fall out anyway, at which point you're left with a shape that is like a vault, and that will be stable. I think at that point, it's not a very big step to say, well, we'll put in a piece of stone which will just complete that shape and leave it there. So in summary, I think that their choice of two stones like that is a response to the natural way that a stone structure would fall into a chamber. It's not necessary. You could leave it away, leave them out, and it would still survive. It's possible to corbel. If you think about, there are many structures like igloos, which are made of ice, but a similar thing where you just go in little steps, and the structure can survive perfectly well without having any stones underneath. It's hard to do it without a demonstration, but the the lines in the sides of the faces they are interesting because, one explanation which is plausible is that they're what we would call a crack inducer. You could imagine that they built smaller pyramids on poor ground, and what happens is the corners are very stiff and strong, and the middles of the faces are actually quite weak. And as the ground moves underneath, you would get a crack down that center line. So traditionally what's done in that situation is you force the crack to appear by making it part of the architecture. So you make a break in the structure. I personally would be surprised if they had done that. And I think that one thing that makes me very think that it's part of the architecture and not part of the engineering is that the pyramid next door, which is almost exactly the same size on almost exactly the same sort of ground conditions, didn't have those in, and it was constructed more or less at the same time. So if they were going to plan for one, they would have done it for both. So my feeling is that it's part of the architecture and not part of the structure. If a structure fails, it curves and then it breaks, and you get a jagged line on what was previously a curved face. That curvature needs to be quite high to persuade something like a pyramid to break its back. Also, it's inconceivable to me that it would break its back in one direction and also in another direction at right angles. To break itself into four is not something which, that's not a natural behavior. You could imagine it breaking into two, but not into four. It could be like an ocean liner running into some rocks, at which point it breaks. But to imagine it doing that way and also that way at the same time, I don't think it works. Also, I also think it's probably, although the pyramids are very heavy, the stresses that they impose on the ground are not, in engineering terms, very high. It's because it's a big distributed structure. And so the difference between the load in the center and the load in the corners is not so high. And so I don't think it would cause an enormous amount of this curvature. So in a nutshell, I don't think it broke its back. I think that was part of the basic architectural design. Pi is extremely important for everything to do with circular geometry, spherical geometry, anything to do with angles. Pi is this magical number. Without it, we couldn't do a lot of the Palladian geometry. It would be impossible to have Roman arches. It would be impossible to have circles. I think it's the relationship of the circumference to the diameter of a circle. I think the golden section, to me, is a little bit of an artificial construct, personally. I know you can find lots and lots of references to it in nature. And I know that the Fibonacci series and all of the other things gradually lead you towards the golden section. And from a mathematical point of view, I think it's very interesting. I personally don't think that it's right to design buildings or structures on some artificial construct just because it happens to be found in one particular mathematical progression. So people who use the Fibonacci series to design buildings, I think, are frankly wasting their time, because why would anybody want to make a building look like a mollusk or a snail? And actually that's where you end up if you follow the spiral geometry too closely. To build things so accurately such a long time ago is it's frankly amazing. It's only in the last 10 or 20 years that we would be able to approach that precision easily. And even now, I think most people would say it would be too difficult for most builders to get anything like that accurate. You need a special skill to be able to do it. So to do it 2,600 years ago is to imagine how they did it with basic technology is very difficult. And I personally think that they would have chosen the things which change the least, and they would have had an understanding of those, which is why I think they would have used things like light as their measuring system rather than anything more physical. Lots of people have attempted to find a way of moving these big pieces of stone, and most of the physical evidence is that the easiest way to move it is on rollers, or sometimes skids. But rollers, I think, is a way that does seem to work, and it's a relatively repeatable method. And the problem with rollers is that the gradient starts to work against you, and so you need more and more people to move it. The steeper the gradient becomes, but it still works. I can't imagine any other device, a ramp and rollers, but the shortest ramp you can, using the existing structure as much as possible, seems to me to be the least painful way of doing it. I mean, they're all pretty painful. I can't imagine a machine that would do it in Egyptian times. I mean, nowadays it would be possible. I mean, you can lift. Nowadays you could lift with a large crane, like the ones they use to build these buildings in London or anywhere. You could lift 10 tons at a distance of, say, 40 or 50 meters. So one big block 50 meters away. That doesn't get you to the middle of the pyramids. So you would, even if you were doing it today, you would need multiple cranes, and it would still be a difficult task.
Ah, hélicoptère. Ouais, j'ai des photos à montrer maintenant pour...
Sur la phrase, juste la fin.
Oui, juste la fin. Ouais. Pardon.
Il parle des actuels.
Hélicoptère.
Yeah. Nowadays we could lift stones of 10 tons to a reach of maybe 50 meters, to a height of 100 meters with very large cranes. But I mean, that's a huge piece of contemporary technology. The Romans could lift stones of 10 tons, small distances, using very small timber cranes, and they had the technology of pulleys. So they could magnify human and animal effort using pulleys. The Egyptians, as far as I know, didn't have pulleys, but they did have rollers and they had levers and they had lots of people. So I think it was a combination of all of those things. If you only have those tools available, pretty much the only way you can get the stones up is up a ramp, I think. Move very large blocks very high is obviously extremely difficult, and I think the only way that could easily be done, the only way it could be done is using a localized, probably a spiral ramp. I think you shouldn't underestimate how much effort is involved in preparing the surfaces of each of the blocks. And there's a balance to be struck between the size of the block and the number of preparations of the surface. If you have too many small blocks, you have millions and millions and millions of surfaces to prepare, and that takes a very long time, even though it might actually be easier to move them up. If you have one enormous block, you have less surfaces, so it's easier to prepare the block, but obviously much harder to move it. So the Egyptians, I'm sure, were very pragmatic people, especially as it was very hot, and so they would strike this balance between the largest block that they could move, which would give them the least number of surfaces to prepare. So in a nutshell, what you're trying to do is you're looking for the biggest piece that you can possibly move, and that will, in the grand total, give you the least amount of work to do. Especially if you look at that little tiny one there, look at that little piece there. There's no way you would ever cut that in a quarry.
Yes.
It would just get knocked off when you put it in a position. So, and I think I think this was all rough. This was rough. They cut these surfaces and these surfaces, and then came and cut it afterwards. And it's very good because it gives you a key, which actually from earthquakes it gives you a very strong structure. I've been here, and I thought it was an amazing place. Sacsayhuaman in Peru. You look at these blocks of stone and you can't imagine how they ever could have got them into position in such irregular shapes. What's amazing about it is that we couldn't do it now. And this was 500 years ago. If you imagine the Egyptians, 2,500 years ago or so. I mean, I've seen people say that they had a special chemical which dissolved the surface and things like that. Ollanta Tambo, I haven't been to, but to me that's not quite as profound. I can see how that was done. That's an easier. Ollanta Tambo is an easier construction. They're larger pieces, but they're more regular. So I think that's what's amazing about the Inca stones is that they would have to held them in position to make the surfaces match and then lower them into position. Now, how you hold them into position and then move them when you have no machinery, I don't know.
Easter Island.
Oh, Easter Island. I haven't been there. The other thing that these projects tell you is that they were the material was very precious to them, because it would have been easier for them to cut rectangular blocks and waste a lot of material and have everything fit together relatively easily than it would have been for them to carefully fashion every single one as an individual piece. So it also tells you that labor was very cheap. I don't know if you look at that one, which is also Ollanta Tambo, so Machu Picchu. Where I have been there. It's near, yeah, it's 20 kilometers away, isn't it? This is more regular. It almost looks as though whoever got there first had the choice of the shape. So the man who put that block down, he made the best he could out of the material he had available. And the man who put that block did the same, and they didn't even talk to each other because there's a big step there, there's another step there. So we have in this situation, three different people come along with three different blocks, and they just join them together as best they can, and then they walk away. And then three more people come along with their blocks, and they have no choice, they're forced to fit them into whatever has been left by their predecessors. That appears to be what happened. I mean, it's a very strong earthquake-resistant structure. If you when they have earthquakes in Egypt, they have very strong earthquakes in the Andes in Peru, and if you look at the Spanish architecture which followed after these Inca structures, many of the Spanish buildings have fallen down, and the Inca structures have survived very well. So it's a tremendously robust system, and it was built to last for thousands and thousands of years. If you imagine doing this using modern technology, what you would do now is you would, apart from the fact you would try to cut all the stones roughly the same size, you would then put a layer of something liquid, a mortar in the gap to fill the gap, to take up all the irregularities. And if you put it in here, you could make a wall that would still be a wall, but it wouldn't be as strong. It would be weaker, because the mortar is a plane of weakness. And similarly, in the pyramids, they were done without any mortar, and it gives them tremendous strength, but also a huge burden on the people who are making them to make all of those joints so precise. I mean, I love stone architecture. I think it's and stone engineering. And the thing I really like about it is it gets better as it gets older, and so far we haven't managed to invent any material that mankind hasn't managed to invent a single material which lasts as well as this stuff. It's amazing, but we haven't done it yet. Well, if this was if you were Charles Darwin and you were thinking about the history of evolution, you would look at these examples of stonework and masonry, and you would say either it's one evolutionary stream, the same stream, in which case these people all knew about each other's work even though they were separated by thousands of years, or you would say there are 4 parallel streams of evolution going on, and to get the same answer, and they're very similar, to get the same answer in 4 parallel streams makes it, to me, seems very unlikely. It looks as though somehow they were talking to each other through time. So I'm guessing that it's hard to imagine that the Incas went anywhere near Egypt. I find that a bit hard to believe. I can imagine. I suppose nowadays we have a series of techniques that people use called evolutionary algorithms, where you set a series of basic rules, and you allow a computer to go away and work out an optimum evolutionary solution. And nowadays we have a technique called evolutionary algorithms, which uses principles of genetics to get architectural and engineering answers. So you set a computer a series of simple tests, and it will invent the best fit to the problem that you're setting. And I can imagine if you look at the Incas, the Egyptians, the people on Easter Island, and other people working in stonework, that they were all trying to solve the same problem, because they have a natural material and they're trying to make structures out of it. So they find the best way to carve it. And if no one has ever invented mortar and a way of jointing, then you have to fit the stones together somehow. So at that point, perhaps you end up with this irregular but perfect workmanship, and they could evolve separately. Who knows?
Yes, but the small.
I know,
small
but
piece.
that's because, well, the small pieces. I think a child of 4 would have done that, because if you have if you have a piece of stone and another piece of stone and another piece of stone, and it's very hard to work with it, and you have a little tiny gap left in the middle, and you think, I've got a piece of stone just over there, just the right size, I'll just put it in, and that's what you do. And I can see the cogwheels going around on Easter Island, and the same thing. I mean, it's physically very hard work working with stone, and extremely heavy, extremely hot, extremely dusty, and so you're looking for the economy of effort. And if you have a piece which fits that hole, that's what you use. So I'm not surprised to see that. I think this monumental masonry construction is a sort of natural answer to one particular set of problems, which is how to build temples, how to build defensive structures, how to build powerful structures. If you change the problem, then you would end up with a different solution. So the fact that it's the same sort of masonry construction has evolved in different places is in response to perhaps the same need. As soon as you decide that you want to make something lighter and particularly transportable, you need something which might be a framework technology, and that leads to a whole different evolutionary branch which goes away from this and into the world that we now occupy, which is the world of frames, skins and shells.
Ok.
And helicopters and airplanes, and trains,
On a plein.
boats.
Ok.